You're about to experience the most extreme journey imaginable, falling through every layer of the sun. But your death isn't the interesting part. What happens to your atoms is where things get truly mind-bending. Our descent will challenge everything you think you know about matter, energy, and the laws of physics themselves. And it starts with a deceptively simple question. What would happen if you could fall straight through our star? Most of us think of the sun as just an impossibly bright ball of fire in the sky. But that familiar yellow disk hides layer upon layer of physics-defying extremes. Each region we'll pass through rewrites the rules of reality in ways that would make science fiction writers blush. And surprisingly, the surface, that dazzling layer we see every day, might be the least interesting part of our star. Let's start our descent 93 million miles from Earth, where space seems calm and empty. But even here, the sun's influence is staggering. Every second, it bathes Earth in more energy than humanity has used in our entire history. Those innocent-looking sunbeams crossing the void carry enough power to vaporize a block of ice the size of Los Angeles in under a second. Yet somehow, we experience this cosmic fury as nothing more than a warm day at the beach. That's our first clue that the sun operates on a scale that defies human intuition. As we accelerate toward the surface, solar gravity takes hold. The sun's mass is so enormous that it creates a gravitational well 28 times deeper than Earth's. Its pull is strong enough to keep entire planets in orbit and bend space itself. Our theoretical fall would reach speeds of over 600 kilometers per second, fast enough to cross the United States in less time than it takes to snap your fingers. At these velocities, the air around you would become plasma before you even touched it. The sun's outer atmosphere, the corona, comes into view. And here we hit our first major physics paradox. The corona is millions of degrees hotter than the sun's surface, a fact that seems to violate basic thermodynamics. Imagine walking away from a campfire and feeling progressively hotter. This mysterious temperature inversion has puzzled scientists for decades, and the emerging explanation involves magnetic waves that create a cosmic heating system more complex than anyone imagined. But the corona is just the beginning. As we pierce through this super-hot veil, we're about to encounter the photosphere, what we think of as the sun's surface. This is where things start getting weird. The photosphere isn't solid, liquid, or even normal gas. It's a layer of plasma so hot and energetic that atoms can't hold on to their electrons, and this is where our journey takes its first truly deadly turn. Here's what most people don't realize about the sun's surface. The visible light that reaches Earth isn't the dangerous part. The photosphere is pumping out lethal quantities of X-rays, gamma rays, and ultraviolet radiation that would vaporize you long before the heat becomes an issue. Your atoms wouldn't just break apart, they'd be stripped of their electrons in an instant, transforming your entire body into a briefly expanding cloud of plasma. But death by radiation is just the opening act. Below the photosphere lies the chromosphere, where temperatures suddenly jump from thousands to hundreds of thousands of degrees. The plasma here moves in ways that seem to ignore physics itself, creating massive spicules, jets of solar material that shoot upward at speeds of 3,000 kilometers per second. If Earth's atmosphere behaved like this, our sky would be filled with 1,000-mile-high tornadoes of plasma. And we haven't even reached the really extreme layers yet. As we prepare to plunge deeper into the sun, we're about to discover that everything we've seen so far, as violent and mind-bending as it seems, is just a gentle prelude to the physics-breaking reality that awaits us in the sun's interior. The real chaos begins when we enter the convection zone, where the ordinary rules of matter break down entirely. The convection zone is where our journey takes a turn from merely lethal to reality warping. Forget about falling in a straight line. You're now in a realm where plasma moves like a cosmic washing machine on overdrive. Imagine ocean currents, but made of material so hot it defies classification, moving at speeds that make Earth's worst hurricanes look like gentle breezes. These plasma rivers carry more energy in a single second than humanity has produced in its entire history. What makes the convection zone particularly mind-bending is that it completely rewrites our understanding of matter states. The material here isn't solid, liquid, or gas. It's not even normal plasma. The temperatures and pressures create a substance that behaves like a fluid but carries electrical currents powerful enough to generate magnetic fields that can rip themselves apart and reconnect in explosive events we see as solar flares. Your atoms wouldn't just be torn apart here. They'd become part of these massive circulation patterns, joining the very mechanisms that drive the sun's immense energy output. This is where we discover one of the sun's most fascinating secrets. It's essentially a gigantic energy transportation system. The convection zone acts as a cosmic conveyor belt, carrying energy from the sun's interior toward its surface through massive cells of rising and falling plasma. These convection cells are so large that if you could see them, each one would be roughly the size of Texas. The physics at play here is so extreme that it generates sound waves powerful enough to make the entire sun ring like a bell, a phenomenon astronomers call helioseismology. But even these mind-warping conditions pale in comparison to what awaits us in the radiation zone below. As we cross this boundary, we enter a realm where photons, particles of light, behave in ways that seem to defy common sense. The material here is so dense that light itself gets trapped in a dizzying pinball game that can last thousands of years. A single photon generated in this region might bounce around for over 100,000 years before finally reaching the surface and escaping into space. This means the sunlight warming your skin was actually generated when humans were still living in caves. The radiation zone presents us with one of the most counterintuitive phenomena in physics, matter so dense that light moves through it more slowly than sound moves through air on Earth. The pressure here reaches levels that are difficult for the human mind to comprehend, about 100 billion times Earth's atmospheric pressure. At these extremes, atoms are packed so tightly together that they create a maze-like structure that photons must navigate, turning what we think of as instantaneous light travel into an eons-long journey. This region also teaches us something profound about the nature of energy transfer. While the convection zone above moves energy through physical circulation, the radiation zone is so dense that convection becomes impossible. Instead, energy moves purely through radiation, bouncing from atom to atom in a cosmic game of hot potato that would make quantum physicists scratch their heads. The material here exists in a state that we can't recreate in any laboratory on Earth. It's a reminder that the universe operates on scales far beyond our everyday experience. As we continue our descent, the pressure and density keep mounting to even more extreme levels. The temperature rises to about 7 million degrees Celsius, hot enough to make the most resilient materials we've ever created look like ice cream on a summer day. But even these incomprehensible conditions are just a prelude to what awaits us in the sun's core, where the real physics-breaking party begins. We're about to enter a realm where quantum mechanics dominates, and the very foundations of matter are pushed to their absolute limits. And here, at the heart of our star, we've reached a place where pressure and temperature create conditions so extreme that quantum mechanics doesn't just matter, it dominates. The core is humanity's ultimate physics laboratory, achieving conditions we can only dream of recreating on Earth. Every second it demonstrates physics that makes our most advanced fusion experiments look like child's play. The numbers alone are staggering. The core's temperature reaches 15 million degrees Celsius, hot enough to give every single atom the energy of a speeding bullet. The pressure? About 250 billion times Earth's atmospheric pressure. That's equivalent to the weight of 250 billion atmospheres pressing in from every direction. Under these conditions, matter is crushed so intensely that atoms are packed to densities 150 times that of water. Imagine compressing Mount Everest into a space the size of a sugar cube. That's the kind of density we're talking about. But the most mind-bending aspect of the core isn't just these extreme numbers, it's what they make possible. This is where quantum tunneling, one of the strangest phenomena in physics, becomes commonplace. Under normal conditions, atomic nuclei repel each other so strongly that fusion is nearly impossible. But in the sun's core, the overwhelming pressure and temperature create a quantum playground where hydrogen nuclei can actually tunnel through this repulsive barrier, allowing fusion to occur. Here's where things get really wild. Every second, the sun's core fuses 620 million metric tons of hydrogen into helium. In doing so, it converts about 4 million metric tons of pure matter into energy. The ultimate demonstration of Einstein's E equals mc squared. This mass energy conversion powers everything from the photosynthesis in your garden to the wind in the atmosphere. Every living thing on Earth, every ecosystem, every weather pattern, ultimately depends on this quantum dance happening in the sun's core. But the core holds an even deeper mystery. Despite these unimaginable conditions, the actual fusion rate per hydrogen nucleus is surprisingly low. Each proton in the sun's core might wait an average of 10 billion years before participating in a fusion reaction. This perfectly tuned inefficiency is crucial. If fusion happened any faster, the sun would have burned out long before life had a chance to evolve on Earth. It's a cosmic coincidence that makes our very existence possible. The core also teaches us something profound about time and energy. The photons created here will spend thousands of years fighting their way to the surface, but the neutrinos, ghostly particles also produced by fusion, pass through the entire sun in just a few seconds. These neutrinos are so weakly interacting that they could pass through a light year of lead without being stopped. Right now, trillions of them are passing through your body every second, carrying with them direct information from the sun's core. As our journey reaches its end, we've witnessed how our seemingly simple sun is actually a nested set of physics experiments, each layer revealing new extremes and mysteries. From the counterintuitive corona to the quantum playground of the core, the sun demonstrates that reality is far stranger than we imagine. It shows us how the universe operates at its most fundamental level, where the line between matter and energy blurs, where quantum mechanics rules supreme, and where the seeds of life itself are forged. This journey through the sun isn't just about understanding a star, it's about understanding our place in the cosmos. Every atom in your body was once part of a star that lived and died before our sun was born. The iron in your blood, the calcium in your bones, the carbon in your cells, all were created in stellar cores like the one we've just visited. We are, in the most literal sense, made of stardust, and as we return to our comfortable place 93 million miles from the sun's surface, we carry with us a deeper appreciation of the incredible physics that makes our existence possible.